Ew. Alright, it's 2:57. The camera quality is like absolute shit right now, but who cares? So, I was studying about nucleophilicity. Nucleophilicity is the tendency or the ability of a nucleophile to give its lone pair to the electrophile, which is like a deficient group of electron, and nucleophile is basically a electron sufficient, or it has excess of electrons, we can say that. I was studying about one of the effect, like one of the factor that affects the nucleophilicity of a compound. So I have, so there was like one factor called the solvent effect, and I like really liked it. I like personally liked it. So I'm gonna like share it with you all. Okay. So there are three types of solvents basically. First is like polar protic solvent, second is polar aprotic solvent, and third is non-polar solvent. First, the name suggests polar protic solvent. Polar means what? Anything that involves plus and minus is like a pole. Alright, whereas protic means having acidic hydrogen. What are acidic hydrogen? Hydrogen attached to any more electronegative group is called acidic hydrogen. Or we can say hydrogen attached to any more electronegative atom is called acidic hydrogen. For example, in water, the hydrogens attached to oxygen. Oxygen is like way more electronegative as compared to hydrogen and hydrogen. Alright, I'm already speaking in like fast speed. I will speak like this. Alright, and we have hydrogen, and oxygen. And this oxygen is like way more electronegative as compared to hydrogens. We all know that, right? So these two hydrogens are acidic hydrogens. For example, we have single bond OH. In this case, oxygen is connected or attached or bonded with hydrogen in this case. This hydrogen is also acidic hydrogen. We have HF, hydrogen attached to fluorine. Oh my god, so much electronegative, alright. Like this is also a acidic hydrogen. So this is how we identify acidic hydrogen. Now coming back to our topic, which is polar protic solvents. So polar protic solvents, they have polarity and they have acidic hydrogen. Examples of this are like written right below. They are water, they are ROH, they are NH3, they are HF, they are RCOOH. Alright, these are the 5 examples basically. And now comes the fun part. Suppose I have 4 compounds sitting right in front of me in different test tubes. Alright, one is NaF, one is NaCl, other is NaBr, and the fourth one is NaI. So we have sodium as the constant cation in this case, whereas the fluorine, chlorine, bromine, iodine, they are the different anions in this case. And notice how the anions are like going down the group, and down the group the size increases. So the size of iodine is like relatively very big as compared to the size of fluorine, which is like really small. Alright, so now comes the fun part. Now I want to compare the nucleophilicity of these 4 compounds, that which of these compound is like more of a nucleophile as compared to other. Like which one is going to be a good nucleophile, which one is going to donate more like faster electrons. Faster electron is the right word, because nucleophilicity is a kinetic phenomena. It is not a thermodynamic phenomenon. Thermodynamic yeah, I'm sorry guys. Alright, okay. Yeah, so I was saying that we have NaF, NaCl, NaBr, and NaI, and the size is like increasing. Now when I introduce them, as to compare them, I'm going to put them into a polar protic solvent. So what happens to them in polar protic solvent? I want to compare the nucleophilicity in polar protic solvent. So I've put all of them in polar protic solvent, and suppose my solvent is water. Alright, so as soon as I put them in, the water molecules will get around it, they will surround it, and the electrostatic forces of attraction, they're going to play their role in this. Suppose I have Na and I have fluorine, NaF, and then the water is going to come, and because sodium is like Na plus, right? It's a cation, and fluorine is like a anion. So the positive charge on sodium is going to attract the negative charged oxygen. Negative charge what? Partial negative charge of oxygen. And suppose we have hydrogen, oxygen, hydrogen. So if I have fluorine here, so my oxygen is gonna come here and my hydrogens are gonna point out like this. Then oxygen, then oxygen, and oxygen, because the positive and negative are gonna attract each other. Whereas on the other hand, where we have fluorine, which is already negative in nature, the hydrogens which are positive, they're gonna come like this. So I'm gonna have like this kind of structure with fluorine. Here is the oxygen and here are the hydrogens which are positively charged, partially positive charged because of the oxygen present here. And I'm gonna have the fluorine which is like negatively charged. Alright. And they're gonna have attraction between them, and here it's gonna be like this. The hydrogen is gonna be like out and oxygen is gonna be here with Na. Alright, and because of this electrostatic attractions happening, the both of the compound will eventually break into cations and anions. And now I have successfully prepared sodium alag se and fluorine alag se. But the thing is that there is still the water like surrounding it. So now if I'm gonna compare that, which one of them is gonna be a better solvent? Let me get it. Which one of them is gonna be a better nucleophile? So we know that in this case, I've messed up somewhere. I'm gonna cut it. So now we basically have them differently. Now we are studying about nucleophilicity. The nucleophilicity is not shown by the cations, right? They are positively charged. We need to give electrons. So we are gonna take the anions in this case. So we are gonna compare the anions. We're gonna ignore the sodium present in all the four compounds. We're gonna now constantly compare the anions, which is fluorine, chlorine, bromine, iodine, fluoride, chloride, bromide, and iodide. And because the like fluorine, and now when I just now I'm like observing all of them together, and fluorine is here, and let's suppose I have iodine here. Fluorine is like very small in size. Iodine is like very big in size. Because of the small size of fluorine, there will be like more charge density here. Charge per unit area is going to be like way high here as compared to here. Iodine has like very big size, so the charge is going to be more uniformly spread on it as compared to fluorine, which is have like very small size. So fluorine is going to attract a lot of hydrogens to it because of its high negative charge. A lot of hydrogens, a lot of water layers surrounding it, like almost itni zyada solvation effect hoga uske andar. Whereas the chlorine on the other hand, it's gonna have chlorine. Whereas the iodine on the other hand, the lack of sleep is hitting me right now. Never mind. Whereas the iodine on the other hand, it's gonna attract way less water around it as compared to fluorine because of the uniform distribution of charges. So due to the solvation effect, देखो, as compared to it, the size of fluorine is like very small as iodine. So if it was not present in a solvent, the fluorine would have won the game already. Why? Because a better nucleophile wants to reach the electrophile jaldi se. Alright? Are you getting my tutti frutti? Excuse me. So जितना अच्छा nucleophile होगा, it wants to reach the electrophile jaldi se in order to like donate the electrons, give the electrons and make bonds and stuff. So जितना जल्दी ये काम होएगा उतना अच्छा न्यूक्लियोफाइल है because it is a kinetic phenomena. But because a fluorine का size छोटा है, it will face like way less problem in getting to the electrophile because of the size and the steric hindrance. It's gonna cross it easily. Like if I have a very big compound here and there is one site which needs electron, which is like electrophile, and there is fluorine, it's gonna go, and there's gonna be like alright attached to it. So if the size is small, it can actually like very much like go easily to the attacking site, to the needy site, I would say. Whereas if the size of if the size is very big, it will not be able to go to that place. But in this case which we are dealing, we are having solvent. So अब इसके अंदर फ्लोरीन का साइज भाई बहुत ज़्यादा हो गया है because of the solvation layer around it. Because of the solvation layer around it. But whereas we have iodine का size पे इतना इफेक्ट नहीं आया है. तो when we are comparing the nucleophilicity of both of these compound, फ्लोरीन को अब अपने अटैकिंग साइड पे जाने के लिए बहुत मेहनत करनी पड़ेगी क्योंकि उसको पहले अपना ये जो उसने ये हिंड्रेंस उसके पास आ गई है, ये वाटर की जो लेयर है, जो सॉल्वेशन इफेक्ट है, उसको उसे क्रॉस करके जाना पड़ेगा, तब तो वो जाकर अटैक करेगा. Whereas इस साइड पर जो है हमारा आयोडीन, it doesn't have that kind of very much big radius of the water layer around it, so it can easily go there, right, in this condition. So the nucleophilicity of iodine in polar protic solvent is way more than the nucleophilicity of fluoride in polar protic solvent. Are you getting it? जितना big बड़ा होगा, the bigger the better in polar protic solvent. I think it's clear. I cannot give more explanation. So the size of the nucleophilicity of NaI is way more than NaBr and then NaCl, and then the least nucleophilicity strength is shown by NaF. Like, don't mind me if I'm like putting the wrong words. It's like 3 a.m. and I'm like extremely sleepy right now, but I like nights. So when we are talking about polar protic solvent, we have done about it. Now we have second kind of solvent, which is polar aprotic solvent. What do you mean by it? Polar plus minus. Aprotic, there is no acidic hydrogen present in this case. There is no freaking acidic hydrogen present. So are you getting the depth of it? How is it gonna affect in this case? There is no hydrogen present. So let me just give you a few examples of the solvent first. We have acetone, we have dimethyl sulfoxide, we have diethyl ether, we have crown ether, which is also known as cyclic ether, and we have one more also, like dimethyl formide, DMF. Yes, I am not able to understand my own writing, but it's alright, it's alright. Now in this case, we do not have any acidic hydrogen present, so there is no positive thing which is gonna come near the negative. Are you getting my point? Like, we have Na, we had fluorine. The Na is going to be surrounded by the negative parts, but because there is no hydrogen present in it, which generally carries a partial positive charge. So there is no positive thing which is going to come and surround fluorine in this case. Fluorine is not going to get solvated in this case. It's going to be like there only, and whereas the cation part is going to get solvated in this case. The sodium is going to get solvated. So now you have like given fluorine its freedom. Now it's gonna fucking show his potential. So in this case, the fluorine, chlorine, bromine, iodine, fluorine is going to win, because I told you, generally, I mean without solvent, fluorine is like very good nucleophile because of its size, because it can navigate its way through the site to the electrophile, and iodine is not, because of the size. It has like way big size. In this case, you have given fluorine the freaking freedom to go back to its electrophile wali jagah, and without having a layer of water present around it, which it has to cross basically, right? So you have given him his freedom. So guess what? He's gonna take his freedom and he's gonna overpower iodine and everyone there. So the priority order, so like the order of nucleophilicity is gonna be NaF supreme, then NaCl, then NaBr, then NaI. Why? Size. Now there is nothing surrounding it, nothing stopping it, nothing to hold him back. So he's gonna show who he is. He is gonna fucking show he is. Alright, so this is how it will work in polar aprotic solvent. And now the third kind of solvent. We have non-polar solvent. Non-polar. There is not even positive negative present in it. The dipole moment is 0. Mu is 0. Dipole moment. Mu is 0. So the examples of solvent are CCl4, benzene, CS2. Alright. We do not have any hydrogen, you can see. In the previous one also, which I told you, like acetone, the dimethyl sulfoxide, diethyl ether, crown ether, cyclic ether, DMSO, DMF, right? इसमें भी कहीं पे हाइड्रोजन नहीं है, like acidic hydrogen नहीं है. Let me correct. Acidic hydrogen is not present in there because it was aprotic. It was not supposed to be here, so it will not be here. But in the non-polar solvent, there is neither going to be acidic hydrogen nor going to be the plus minus only thing, because it's non-polar, and the mu value is going to be 0 or approximately 0. Alright, so in this case, ionic nature is decreasing and covalent nature is increasing as we go down the group. So what I want to say is, like, give me 1 second. Yeah, so because the solvent here is non-polar, अब polar solvent के अंदर क्या हो रहा था, दोनों polar solvents में there was something present which was able to like break the compound into two parts, like Na को अलग और iodine को अलग कर पा रहा था. Polarity तो present थी, जैसे कि फर्स्ट वाले के अंदर तो there was positive and negative present in both the ends which were like taking them apart. सेकेंड वाले के अंदर कम से कम सोडियम को तो अलग कर दिया, चाहे फ्लोरीन को करने के लिए कुछ था नहीं अलग. देयर वॉज नॉट एनी पॉजिटिव hydrogen like H plus present here, acidic hydrogen present here to take the fluorine apart, but there was negative part present to take the cation alag. So there was like basically it was like divided. But in this case, when we have non-polar solvent, there is nothing here. What is gonna like कुछ है ही नहीं जो उन दोनों को अलग अलग करेगा. There is no force present acidic. So what is gonna happen here? The nucleophile is like very desperate. Yeah, someone please give me electrons. And I think I said wrong. The electrophile is like desperate that someone please. Yeah, I feel like someone is looking at me through the door. It's already like 3:15 already now. Never mind. And I was like saying ki, what was I saying? Yeah, the electrophile is like very desperate. Here, please someone come and give me the electrons. Please at least give me. But then nucleophile wants to give, but he's like, yeah, I'm majboor, I'm not broken apart. If you can come and help me escape this situation and then come to you, I can help you with that. I cannot come here. अभी तक तो nucleophile अपने आप जा पा रहा था, but in this case it's not able to go because there is nothing to, अभी वो अलग ही नहीं हुआ है, compound में ही है, वो तो नहीं आ सकता. तो electrophile को अब अपना गेम अपने हाथ लेना पड़ेगा. He's gonna be like, all right, I'm gonna help you. I'm gonna come to you. I'm gonna fucking help you escape. He's gonna like warn that anion part. He's gonna warn that sodium ka cation wala part. Excuse me, I want this. I want this nucleophile to come and make me stable. I want to get stable. Yeah, I just let him be with me. So he's gonna come. He's gonna stand there. He's gonna do his talking, and then he's gonna take the freaking nucleophile with him. This is what it's going to do. So imagine if I am the electrophile here, and पहले तो मैं ही desperate हूँ कि भाई मुझे कोई इलेक्ट्रॉन नहीं दे रहा है, और ऊपर से मैं देख रही हूँ कि what is this drama going on कि we have NaF, NaCl, NaBr, NaI in front of me, and they're like joined. They're not even like अलग. Are you getting my point? The cations and anions are not even different. So I have to like choose. Like if I have the ability to choose यार which one of the nucleophile I'm gonna choose for myself, क्योंकि मुझे जाकर लेकर आना है, अब मेरे पास ऑप्शन नहीं है, खुद ही जाकर लेकर आना है मुझे अब. तो what I'm gonna do, I'm gonna see कि okay, सोडियम साइज छोटा है, फ्लोरीन साइज छोटा है, they are bonded. Electrostatic force of attraction are gonna be like great in this case, great. And because दोनों का साइज छोटा है, the bond length it's also gonna be like very small as compared to the bond length between NaCl, and then we have NaBr, and then we have NaI. I'm gonna be like, मैं तो हूँ ही आलसी, अब मैं किसको चूज करूँ? मेरे लिए जो तोड़ना आसान होगा, I will just go there, right? It is way easier to break इतनी बड़ी pencil as to compare इतनी सी pencil. So I'm not stupid. I'm already desperate, and I want my work done as soon as possible. So what I'm gonna do, I'm gonna go to iodine, and I'm gonna take him with me because I want my work done. And that's it, guys. In this case, in non-polar solvent, the iodine wins because of its size. It wins because it has way longer bond length and weaker bond between the sodium and iodine in this case. It wins. So the order of nucleophilicity in non-polar solvent is going to be like least NaF. Highest is going to be NaI, then NaBr, then NaCl, and then NaF. This is how it works. Why did it win again? Because मुझे चूज़ करना है और मैं बहुत आलसी हूँ. मैं चूज़ करूँगी जो मेरे लिए सबसे आसान होगा कन्विंस करना, because I do not have that time कि मैं तुम्हारे bonds तोड़ूँ बैठकर. It's easier for me to choose iodine as to choose fluorine because it is like very small and very tightly bonded and very small bond length and very good forces here. Because iodine is like have like very gigantic size as compared to sodium. So the bond length is going to be gigantic too. It's going to be easier to take it. Right. It was like, I mean, when I like first time I read about it, I was like really impressed by this concept. I don't know. It's just easy. It's fun to understand. It's fun to teach. It's kind of that. So yeah, I'm hungry now. But let me just end this video. Bye bye.